Hello, this is part 2 of the Rectilinear Motion introduction. So let me just get right into it. So we left off by saying that the total distance traveled was 28. But let's go back to the problem really quickly because I'm always talking about units. So if I go back to the problem, it says that t is measured in seconds and the position function is measured in meters. So to make this 100%, I'm going to type in, write down meters in this problem. So that's the completion of part 1 here. Now, part 2 of the video is talking about questions G, H, and I. So G is find the acceleration at time t and after 4 seconds. Well, the second derivative of my position function is going to be my acceleration. So part F we did on a piece of paper. Part G, I'm going to do right here. So here's the here's the acceleration function. It's just f of t. And to evaluate this, f double prime of t, the acceleration, at 4, I need to do f double prime of 4. I'm going to evaluate this, and you notice that I have a return error right there. So let me go back and do this. So the second derivative of this particular function up here is, well, let's bring the first derivative up and let me also hide all of this other stuff. I'm going to suppress it for a moment. The derivative of 9 minus 12t plus 3t squared, well, we got some power rule stuff. We got the sum rule, the constant multiplier rule, negative 12 plus 6t. If I plug 4 into that, I'm going to get negative 12 plus 6 times 4, which should be, well, I think you can calculate that. So let me bring back my last little calculation here. It winds up to be 12. Now, what are the units for the second derivative? Well, the units for the first derivative is meters per second, because we're going to divide by the time unit. Meters per second, if I divide that by a time unit to get to the second derivative, it's meters per second squared. So that's what part G is. Now, I'm going to take this one step further. And I want to write this number line idea again. So my acceleration function is negative 12 plus 6t. What is that equal to 0? Well, it's a value of 2. I really don't need Mathematica to do that one. Negative 12 plus 6t is equal to 0. T is equal to 2. So I want to try to write all of this back down a little bit neater than I did before. So what I want you to do in all of these problems, I want you to have a first derivative line, which in this case it's velocity, and a second derivative line, which is acceleration in this problem. So I will label this on the right-hand side velocity and acceleration. Now, my key numbers were 0 and 5. There's a 1 and a 3 that made the first derivative, the velocity, equal to 0. What was the only thing that made the acceleration equal to 0? Well, that was t equals 2. Copying some of these symbols on that top line, I get forwards, backwards, forwards. So I will write down an F, a B, and an F because I did most of the work right over here. Now remember my acceleration function? I'm just going to write it down here in case you didn't know where this 2 came from. It was negative 12 plus 6t. And I said I really didn't need Mathematica to set this equal to 0. I wind up getting t equals 2. So I'll put a positive and negative sign here. So pick a test value. any number between 0 and 2. Let's pick the number 1. Let's go back to the acceleration function. That's what this is. This is the acceleration function, and this is the velocity function. Just keep reminding yourself of that. Take the number 1, let's plug it into here. Do we get a positive answer or a negative answer? Well, negative 12 plus 6, I think I could do that one in my head, is negative. Pick a number between 2 and 5. Let's pick 4. Pick 3. Pick 3.5. It doesn't make a difference. I'm going to pick 4. Negative 12 plus 6t, well, that's positive when t is equal to 4. So why am I doing this? This is really going to help me answering another part of the problem. And the problem that I'm talking about here is actually part I. I am going to skip H for a moment, and I want to do part I. When is the particle speeding up and when is it slowing down? So that's where these number lines come in very, very handy. So speeding up, slowing down. SU, ST, speeding up, slowing down. What I would like to do is transfer each one of these numbers to this line. 0, 1, 2, 3, and 5. This isn't really to scale. I know this distance isn't the same as distance in terms of time. When is something speeding up? Well, the direction of the motion and the direction of the acceleration have to be exactly the same. In other words, the product of the velocity and the acceleration has to be positive to speed up. If the product of the velocity and acceleration is negative, then the particle is slowing down. Think about this. When you're in your car and you're moving forwards, you have positive velocity. You step on your brake, your acceleration is negative at that moment. Do you speed up or slow down? Well, obviously you slow down if your brakes are working. If you're moving forwards and you step on the accelerator, that means you have positive acceleration. You also have positive velocity, that means you speed up. So what does this mean? In this interval right here, between 0 and 1, I have the velocity as positive, but the acceleration is negative. So that product, and I'm thinking of a product here. Positive times negative is negative. What about in this region between 1 and 2? Both the velocity and acceleration are negative, so that's going to be speeding up. So I'm going to put a plus sign there. Negative times positive, negative. That's a slowed down area. Between 3 and 5, I get positive and positive. That is a speed up. So this is a slow down. This is a speed up area. Whoa, SP. Don't know how I did that. SU. Slowed down. Speed up. So that answers part I. So where is this particle speeding up? Well, between 1 and 2 and 3 and 5. And it slows down between 0 and 1 and 2 and 3. So that answers part I. You can summarize this in a sentence or two, but I'm going to leave it as is for right now. So part H. Part H just says graph the position, velocity, and acceleration function. Graph, this should be a fairly straightforward one. So I am going to do part H. Whoops, my bad. Part H, and I'm going to plot 3 different functions. Now what's really nice is f of t, that's the position function. F prime of t, that's the velocity function. And then f double prime of t, that's the acceleration function. So I have the position, velocity, and acceleration function in a list. I still need to tell Mathematica the plotting domain. And in this plotting domain, it's 0 to 5 because that was given in the problem. It says it right up here, 0 to 5. I'm going to Shift Enter. Let's scroll a little bit. And now I have the little bit of issue with which is which. Well, think about what the position function was. That was a cubic function. Which one of these looks like a cubic function to you? Well, to me, it looks like the blue one. The velocity function was quadratic. So that's, let's call that orange. And the linear function there, remember, -12 plus 6t? That was our acceleration function. And that's the entire problem. Again, I hope this was helpful. And if you have any questions, let's talk about them later. See you later. Have a good one. Bye.